Okay, I wanted to finish up some facts about directional derivatives and then talking about uh, tangent planes to level surfaces. Okay, we'll explain what that means in a few minutes here. I called this lecture 34, though it may not be. Whatever. Okay, directional derivatives. Do you remember this? Cap D subscript U hat of F. Okay, that's one of our notations. Oh, I should mention another notation here. But anyways, this is the gradient of f dotted with u hat. U hat indicates what? That's a unit vector. Sometimes people would do this too. Here's an old notation here. People will go the partial derivative of f with respect to u hat. This doesn't really make that much sense to me, but that is an old notation. All right. All right, I guess I'll just throw that in case you see that in some old book sometime. Okay, z equals a function of x and y differentiable, so this is some nice gradient here. I'm going to probably even do this in the future here. This gradient f, these functions are even continuous here. Okay, that's what we'll be doing in the future. But right now, here's a question. In which direction would you move in order to maximize your rate of change? Okay, at the point, some fixed point AB. Okay, in which direction would you move? That's just a question here. Okay, all right. So you're standing in the XY plane, and you imagine this surface above you, where what? Z is a function of x and y. Okay. Now you could, which xy direction, now imagine being up on the surface itself, which direction relative to the xy plane would you move in order to go up as quickly as possible? Okay? All right, that's the question. Well, here's what we're going to do. The directional derivative here at AB is given by this thing. We know that's the rate of change in a particular direction. Okay, that's the gradient of f at AB dotted with u hat. Now, do you remember the dot product has the following property? It's actually what? The magnitude of the two vectors you're dotting, the product of the magnitudes of the two vectors you're dotting, times the cosine of the angle between them. Okay, alrighty, remember that? Okay, now that would be what? The magnitude of the gradient at AB times the magnitude of u hat times the cosine of the angle between them. The magnitude of u hat is 1 because that's a unit vector. Okay, so the theta here is the angle between the gradient and u hat here then. This would be what? The magnitude of the gradient at AB times the cosine of theta. So that's the directional derivative. Okay? Now, that's going to be different for different u's, right? Different thetas, in other words. Okay? Now, remember the gradient at AB. I'm going to assume that's not 0, by the way. The gradient at AB is going to be some fixed vector because you've evaluated it at the point AB. The only thing that's changing is really u, and since I'm talking about theta being the angle between u and that fixed vector, gradient vector, we think of theta as being variable here. Now consider that, okay? I'm trying to maximize this thing up here, the directional derivative, right? This is fixed. What I would really need to do then is what? Maximize the cosine of theta. Which angle theta gives me a maximal cosine value? Well, this will be maximized with what? By the way, remember theta is between 0 and pi. This will be maximized when theta is equal to what? 0. Okay? So that means, wait, if the angle theta is 0, is the angle between the gradient and u hat, well, the direction that and u hat, then the direction I should move is the direction of the gradient, okay? Thus, u hat should be the direction of the gradient. So I'm going to call that u hat sub 0 here. But that's what? The gradient divided by its own magnitude. That would be the direction that you would want to move. So I would just say that is the direction of the gradient Okay, that's the easiest way to say it. Okay, the direction of the gradient. Okay, all right. Well, what would be that maximal value of that directional derivative, by the way? Well, what happens, what's the maximum value of the cosine? The maximum value of the cosine is 1, as we said, when theta is 0. And when I substitute that value in the formula here, or evaluate it at theta equals 0, I get the magnitude of the gradient times 1. So the largest possible value of the directional derivative would be what? The magnitude of the gradient. So the magnitude of the gradient gives the what? Maximal rate of possible rate of change. The direction of the gradient is the direction you want to go for maximal increase in the value of the function. Okay? Okay, so we say this. Property of the gradient, it provides the direction of maximal increase of the function. Sometimes people will call that steepest ascent, thinking of it as like walking along a hill. Okay? By the way, you can prove this exercise for you. The negative of the gradient gives the direction of the steepest descent or maximal decrease. Okay? If you want to go down as quick as possible, which direction would you go? You'd go in the opposite direction of the gradient. Okay? Alrighty. All right, that last one could be an exercise for you. Let's talk about something else. Let's talk about level surfaces. Okay. Now I've got a function cap f of x, y, and z. Okay? All right. And I'm going to assume this is nice and differentiable here. Okay? So I'm going to imagine this being embedded in 4 space. So I've got what? W equals function of x, y, and z. Yeah, we can't actually visualize that unless you're Roger Penrose or somebody like that. Okay? All right, but I'm going to imagine doing that and intersecting with this hyperplane. Okay? So I've got 4 dimensions, x, y, z, and w. If w is fixed, w is k, then I'm going to call that a hyperplane. Now imagine the intersection. I know it's hard to imagine, but the intersection of these two would be what? What we call a level surface. It's a set of all points f of x, y, z is equal to a constant k. So that's a level surface. Okay, what would be examples of level surfaces would be something like this. How about x squared plus y squared plus z squared equals 9? Okay, what would that be? X squared plus y squared plus z squared equals 9. That's what we call a level surface. Okay, that would be what? That would be a sphere of radius 3 centered at the origin 0, 0, 0. Okay? All right? Do you notice that z is not written in the form z is a function of x and y? Because this would what? This would not pass the quote-unquote vertical line test in the sense that any line orthogonal to the xy plane would not intersect that surface at a single point. It would actually generally intersect the surface at what? 2 points, okay? All right. Generally, there are cases where it intersects at 1 point, just on what? Where the xy plane and the sphere intersect, or places where it doesn't intersect at all. But you see that z is not a function of x and y explicitly here, okay? You would have to actually break that into what? 2 separate surfaces, the upper half of the sphere and the lower half of the sphere, if you were going to do that, okay? But anyways, and you can, this is a pretty well nice behaved function of x, y, and z here. You could imagine a really ugly one where it's next to impossible to solve for z here. That's why we'll use more of an implicit way of finding the tangent plane to such level surfaces, okay? But anyways, cap of x, y, z is equal to cap k there. K is constant. That's what we'll call a level surface. We're going to assume it's nice and smooth here, okay? I'm going to have 2 points on that level surface. P, which has coordinates a, b, c, and Q, which has coordinates a plus delta x, b plus delta y, c plus delta z. They both lie on that level surface. This should be looking familiar here. I'm going to find the equation of the tangent plane to that surface. Okay, the cap function evaluated at Q minus the function evaluated at P are both going to give you k, so their difference is 0. Since f is assumably differentiable function of x, y, and z, that means what? Change of this kind is going to be what? cap f sub x at ABC times delta x plus cap f sub y at ABC times delta y plus cap f sub z evaluated at ABC times delta z plus these error terms here, epsilon 1, epsilon 2, epsilon 3 multiplied by the change in x, the change in y, change in z. The epsilon 1, epsilon 2, and epsilon 3 go to 0 as the changes in x, y, and z go to 0. So we have three independent variables this time, x, y, and z. Okay, so here's what the idea here to find the tangent plane. Now suppose that these points lie in a smooth curve on the surface parameterized with arc length s. Okay? Then I could talk about what? Dividing by delta s all along that curve. Okay? All right? So I have f sub x evaluated. This is actually evaluated at a sub b, a, b, c. Each of these are. Okay? And this would be what? The change in x divided by delta s, the change in y divided by delta s, the change in z divided by delta s, plus our error terms altogether times delta s, okay, going to 0. Taking the limits as delta s, if you want to play around with this term, you can see why it's up here. Okay, or if you wanted to, just divide by delta s in each one of those. Okay, now taking limits as delta s approaches 0, that would mean what? The point Q is approaching the point P along whatever that smooth curve is on the surface. Okay, as delta s approaches 0, this means what? F sub x at ABC dx over ds plus f sub y at ABC dy over ds plus f sub z ABC dz over ds would go what? Equals 0, right? Because this would be going to 0, the error. Okay. Do you recognize we can write this as what? A dot product? This is actually the gradient of cap f evaluated at ABC dotted with dx over ds, dy over ds, dz over ds is equal to 0. Now, do you also see this as what? This is the unit tangent vector to that curve embedded on the surface, okay? Because I'm using what? Arc length as a parameter, so that's t hat. Unit tangent vector dotted with a gradient is 0, and this holds for what? All smooth curves through that point on the surface. Okay, I took an arbitrary smooth curve on the surface, so I drew a couple here. Here's my surface here. Okay, it doesn't look very good. But then I've got my point ABC here. It's the red dot. Okay, I've got, you know, any smooth curve going through there has the quality that what? The gradient dotted with a unit tangent vector to that curve, and there's infinitely many such curves, but it always ends up giving you 0. What would that mean then? That would mean the gradient of cap f at ABC has to be what? Normal to the surface. Okay? Normal to the level surface. Okay? What would that mean? Well, if I imagine gathering all those tangent lines formed from these, what? These tangent vectors here, that I've actually got a normal for the tangent plane to the level surface. That being the gradient. Okay, so you can see this is just like we saw in a previous lecture there, where we had what? A gradient in 2 dimensions being orthogonal, or I should say normal, to what? The level curve. The gradient in 3 dimensions here, or a function of 3 variables, is what? Normal to the level surface. Okay? Now let's just take an example here. Okay, find the Cartesian form. I think I've gone over to using the term normal form, okay, rather than Cartesian, okay. So on the exam, I'll probably say normal form. Anyways, find the normal form of the plane tangent to this nice smooth surface here at the point 1, negative 1, 3. I promise if you put those in there, well, if I did my arithmetic correctly, yes, I did, that this point actually lies on this surface, okay? And you could graph that surface if you want to with GeoGebra or something. I want to find a tangent plane to the surface, okay? The clue is to find a normal to the surface, and then I'm in business, okay? I take my function, cap f of xyz is going to be x squared minus 2y squared plus 5z. My constant, which what I was calling cap k there, is 14, but that's not going to matter too much. Yeah, the important thing is this point lies on that surface, okay? Find the gradient of cap f. That would be what? 2x minus 4y, 5. X, y, and z are independent variables. So when I differentiate with respect to x and hold y and z constant, I get 2x, and differentiate with respect to y by holding x and y constant, and so forth. Okay, so those are those partial derivatives. So I'm calling this n here, n bar. It's probably not going to be a unit vector, so I use a bar on it, but it's going to be the gradient evaluated at 1, negative 1, 3, and I got 2, 4, 5, okay? Now I've got a normal to my tangent plane, right? And I've got a point of my tangent plane being what? The 1, negative 1, 3 up here. Okay, so if I imagine an arbitrary point x, y, z on that tangent plane, the vector from my starting point at 1, negative 1, 3 would be the vector, you're right, brackets, okay, angled brackets, x minus 1, y minus negative 1, or y plus 1, z minus 3, and dotted with what? That fixed normal vector should be 0. So that's what? 2, 4, 5. So that's what? 2 times x minus 1 plus 4 times y plus 1 plus 5 times z minus 3 is equal to 0. Put it all together, I get 2x plus 4y plus 5z equals 13. That is a piece of cake. Okay? So go back and look at that. You guys were going to use to get the normal form of the tangent plane to the surface. We'll go ahead and use the gradient of the function f of x, y, z. Now, here's a quick question. Is this method consistent with our previous method for finding the tangent plane to z equals f of x, y? Remember that? Okay? Remember that? Here's our old method. We went like this. Well, we would say z has the following tangent plane. Okay, z is f of ab plus what? F sub x at ab times x minus a plus f sub y ab times y minus b. There I've written my answer in the form z is a function of x and y. Okay? Alrighty? That's how we did it before, right? Remember that? Okay, here, what's our new method? Z is a function of x and y. Ooh, I need to think of that as a what? A level surface. This isn't a level surface here. Do you see up here? That's not a level surface. That's a surface, but it's not a level surface in the sense you're not thinking of it like we did up here. Right? This is a level surface. This is how we consider it. Okay, it's going to be looking something like this. Okay. All right. So let's come back here. But we can think of this as a level surface. Okay. All I'm going to do is subtract z on each side. How about that? Then I've got whatever my little function f, small f of x, y minus z is equal to 0. And then if I call my function little f of x, y minus z being my cap function, cap f of x, y, z being that's a function of x, y, and z, right? I see x, y, and z there. Okay, cool. And then I've got a constant cap k being 0. I can think of it now as what? As a level surface. What would my method, how would my method work now, my new method? Let's see, I would take the gradient of cap f, so I'm going to what? Differentiate this with respect to x, right? Holding y and z, x, y, and z are independent variables. So here I'm going to hold y as a constant and z as a constant. When I differentiate this whole thing, cap f, with respect to x, when I differentiate z with respect to x, I get 0. So I get what? Small f sub x for my derivative of cap f sub x, okay? And the same thing with y, okay, same reasoning. what happens when I finally differentiate with respect to z? I would just get what? -1, because x, y, and z are independent variables. Little f of xy, there's no z in there. So whatever it is, when I differentiate with respect to z, I get 0. So I get 0 minus 1 is 1, minus 1. Okay, so my normal to my surface would be the gradient of cap f evaluated at AB, and the function evaluated at AB, that's the z value, right? Okay, that would be this. Okay, and then what? I would dot this normal with x minus a, y minus b, z minus my function evaluated at AB. Put that all together, and you take your dot product, and I'll write it in the form where z has been isolated instead of my typical normal form. And I get little f of AB plus f sub x at little ab times x minus a plus f sub y at ab times y minus b. My goodness, that's exactly my old form. Okay, so these two methods are totally consistent. So that means, if you remember this trick that I've used on this problem, if you forget the old way of doing it, right, and you just remember this generalized way of using gradients to find what? Tangent lines or tangent planes, depending on the context, right? Then you should be in good shape here. Okay? Well, I hope you understood that.